There are many applications that take advantage of the wave interference properties of light. One of these is the Michelson interferometer. An interferometer is an optical device that can measure the wavelength of light by utilizing the interference between two light waves. The figure shows the geometry of a Michelson interferometer. Light waves emitted by a monochromatic light source strike a beam splitter, so called because it splits the beam of light into two parts. The beam splitter is a glass plate, the far side of which is coated with a thin layer of silver that reflects part of the beam upward as wave A in the drawing. The coating is so thin, however, that it also allows the remainder of the beam to pass directly through it as wave F. Wave A strikes an adjustable mirror and reflects back on itself. It again crosses the beam splitter and then enters the viewing telescope. Wave F strikes a fixed mirror and returns, to be partly reflected into the viewing telescope by the beam splitter. Note that wave A passes through the glass plate of the beam splitter 3 times in reaching the viewing scope, while wave F passes through it only once. The compensating plate in the path of wave F has the same thickness as the beam splitter plate, and ensures that wave F also passes 3 times through the same thickness of glass on the way to the viewing scope. Thus, an observer viewing the superposition of waves A and F through the telescope will see constructive or a destructive interference pattern depending only on the difference in path lengths dA and dF traveled by the two waves. If the distances dA and dF are equal, then waves A and F travel the same distance, i.e. the optical path length difference is 0, and the field in the telescope is bright due to constructive interference. However, if the adjustable mirror is moved back, say a distance of 1/4 wavelength, then wave A travels a further distance equal to twice this much, or 1/2 lambda. Thus, the two waves arrive at the telescope exactly 1/2 lambda out of phase. This satisfies the destructive interference condition, and the field in the telescope appears dark. If the mirror is moved continuously, then the difference between dA and dF keeps changing, and the field in the telescope changes from bright to dark, etc., as the constructive and destructive interference conditions are satisfied in sequence. By carefully measuring the changes in the distance dA between successive bright and dark fields, the wavelength of the light can be accurately determined.